Namaskar, welcome back. So last uh, discussion where we left was on the fault topography, and I was discussing the example from Japan, one of the earthquake which resulted into the formation of the fault scarp, and over the time how people uh, since the memory is very short, we know that. And we have a habit of forgetting things very quickly, and this exactly happened in Japan. So earthquake topography was not taken into account, and then the houses or the civil structures were being constructed on the active fault scarp, which is not permissible. However, later they uh, take they took into account this type of constructions, and they restricted people to go for any development across the active faults, and that happened after 1995. Okay. So 1995 was the major earthquake in Japan, that is the Kobe earthquake, and after that they realize that precautions needs to be taken to avoid destruction in future. So let's move further and then see that uh, whether we recognize this type of structures on the surface of the earth. Okay. So as this question has been posed here, that can we identify the active fault now, and that is after almost 100 years. Okay. So the answer was, of course, no for the local people, but scientific community, yes. Okay. And because of this short memories and having a potential habit of the human habit that you forget things very quickly, this has happened. Okay. Now this was uh, the slip which took place on thrust fault, and the within reverse component here, as well as it had an strike slip component, and this was in during 1999 Taiwan, that was Chichi earthquake, where the fault was going through the your playground or the pavilion, and then the racing track was been displaced, and other structures were also been affected. And I remember that there was one dam which was across this fault which also got damaged. So this is a typical surface expression of the faults uh, when have the displacement which results into the fault topography. So this what we have been learning since last couple of lectures about the topography. So this is your fault scarp actually. So of course the surface on either side of the fault, and the fault trace goes over here. This goes somewhere over here. Okay. Now this was of course a flat surface because it is a racing track which got displaced. So if you put a section here, then you will be able to reconstruct that this is the topography what we are having, and the fault is sitting somewhere here. This portion has gone up. Okay. So this is your hanging wall, this is your foot wall, and this is typical of your thrust faulting. So this was from Chechi earthquake. Again, another photograph of that, almost uh, 1 to 2 meter, 1.5 to 2 meter displacement, vertical displacement occurred along this. Another photograph of the full fault trace you can see over here. This goes, the fault goes like this, and this is your fault scarp. Now, as we have discussed in one of the lecture, that after the earthquake this fault scarp will be exposed to weathering, and that may result into the almost like there is no evidence, everything has been eroded away. So possibilities are high that if the recurrence is very low across this, because it is not moving uh, in a very short period, so this may get eroded. Okay. At the same time, you may talk about or say that there was an human interference over. So anthropogenic activity can also result into obscuring or completely removing the evidence of the past earthquakes. Okay. But the case here, eh, in the Indian plate, okay, was quite different. This fault is known as Thanda active fault, and which was identified by Nakata in 1999. And Nakata is a person who gave the concept of active fault in India, and he's from Japan, Hiroshima University. So he submitted this report of the active faults in Pakistan. Now, when this report was been submitted to the Geological Survey of Pakistan, they did not believe. They did not believe in active faults. Okay, and same goes, I would say, that in the Indian side also. Okay, so it is hard to convince the structural geologist that such the ongoing deformation can have a clear cut manifestation on the surface. So, having his background from Japan, and he worked for his PhD in India on active faults, he tried to identify the active fault signatures, okay, in Pakistan region also. So, 2005 was the earthquake which proved his findings. The 2005 was Muzaffarabad earthquake, and that took away almost 80,000 lives. Okay. So what you see in the photograph right now is, of course, one is the landslides. Okay, over here. So you have landslide, and then you have this topography where the houses are been constructed over here. These are shelter houses, and then the topography runs somewhere like this. Okay. So just recall the Chichi fault scarp. Okay. So you will be able to understand that this portion, the base of this is your active fault trace. Okay. So this is an active fault trace, and this is your fault scarp. So again, if you put in section here, this is a typical of a thrust fault. So you have an hanging wall here, you have a footwall here. Now, usually it has been well understood and experienced also that the footwalls usually have less acceleration, whereas the hanging wall, since it will move, okay, it will have higher ground acceleration. Okay. So this also we are talking here about the ground acceleration. So you will have higher ground acceleration on the hanging wall side. Of course, the house which is sitting here was marginally, like we can say, it was safe, and as well as this house, if you see, it was safe because it was not multi-story, single-story house was there. But what you see on the hanging wall side or along the on the scarp, all this are the roofs of the houses which were which existed before the earthquake. Now the question is that suppose we take this as an the elevation of this house, okay, maybe around say uh, 3 meters or so, okay, then the height of the scarp is much much higher, okay. So the question is that whether this scarp was created during a single event or this indicates a multiple event, okay. So that question we can ask whether this scarp, okay, maybe around, let's say around 15 to 20 meters, okay. I'm just roughly putting it. So this 15 to 20-meter scarp was generated in single event. This is our question, okay. So if we question about the height, then the answer is no. It is not possible that this 15 to 20-meter high or maybe more than that, okay, was because of your single event. So we are not very sure about that, okay. But the possibilities are less, okay. So less possibilities that this is a single event scarp. So this we can infer at least that this is the height what we see is because of cumulative slip on this fault, because whenever there is, like for uh, one earthquake this has been lifted, then second earthquake if you say, then the height will be more. So this keep on adding, okay. So height keep on increasing, okay. So this elevation what we see is not the single event. That means that this area had earthquake in past, okay, and was during 2005. Potentially, yes, next earthquake in near future. So this fault has potential to host big earthquakes of magnitude, because the magnitude was around 7.6 moment magnitude or 7.8. So this fault, what is thunder fault, has capability or potential to host large magnitude earthquakes in near future also. Scientific groups did paleoseismic investigations, what we usually do in India also, and they were able to identify that this was not the only earthquake which was hosted by this thunder fault. In it hosted many more earthquakes in the past also, okay, and will host in future also, and that is the definition of what we call active fault. So there are ways to identify the fault topography, as we have discussed in one of the lecture where we were talking about the field techniques, okay. So we suggested you that we can use high resolution satellite data. And then we also suggested that if we can use this in like anaglyph to see the terrain in 3D, that will be really good actually. Okay, but sometime this technique or the method using high resolution satellite data, and that too also stereo pair, because this will give you the 3D vision. This has limitations, okay, because mostly what the data which we are using are the panchromatic data, and it cannot penetrate through the vegetation and all that. So, we will not be able to identify. So, limitations if we see of the satellite data, then it cannot penetrate through the vegetation, and if you have thick vegetation, then it is difficult. Further, if the fault topography is been camouflaged because of your population, that is the over construction, and plus we can say that modification. Now, in such cases, LIDAR technique is effective. This is the image which you are looking at on the screen is the LIDAR image, where after collecting this data, they have been able to remove the vegetation part, and one can see clearly here that the people have constructed their houses even across that, okay, because they are not aware of uh, the active fault, because the recurrence interval usually is very high, okay. So, recurrence interval for large earthquakes is almost like 500 to 600 years, okay. This is mostly in Himalayas they have identified, and even in Andaman and Nicobar, the mega subduction zone or mega thrust subduction zone earthquakes, the recurrence what we found was around 700 years or so, okay, 400 to 50 to 700 years. So, it will take time, and in centuries this type of features will be almost you can say that they are removed or modified and they get eroded. So, whatever the minimum topography which has been left out, to that what we call residual topography, and after the erosion, after the modification, that can be picked up by the LIDAR mapping, okay. So, in most of the countries now, of course, the LIDAR mapping is very expensive. So, what they do is that if the scientists are unable to identify the trace, and they infer the trace and try to do the site specific LIDAR mapping, okay. So, here the fault goes along this line, which is very clear, okay. Even a layman can identify this fault, okay. But across this there has been some sort of a very important constructions which have been done, of course, and then houses are just sitting close to that, okay. Now, this part we have already discussed, but yes, a part of this is the oblique slip what we are talking about, okay. The oblique slip faulting, okay. So, this is typical of oblique slip faulting. So, oblique slip faults, okay, as we have discussed, that they can have the combination of what we did on that day was that we said, okay, one is your uh, thrust fault, we can say, okay, or normal, then second is your normal, and third is your strike slip. So, you can have combination of this or you can have combination of this. Okay. Now, in this case we have combination of normal fault and the strike slip, where the the block, this block, okay, which is the hanging wall block, okay, because this has moved and this will be your foot wall. So, hanging wall has moved along this line, okay, up to this point and this point are same, okay, as well as it has moved laterally along this one. Okay. So, it has two components here. So, where if you look at on the description side, and that will make things easier. So, A, that is your red line, is your net slip, okay, because net slips is always measured with the two reference point, or you can say with the reference point of the upper or the lower bonding surface. Okay. Now, upper of the lower bonding surface, when I say, then this is your bonding surface between, for example, this is your A unit and this is your B unit. This is A unit and this is your B unit. So, based on that, one can talk about the net slip. Okay. So, A is your net slip, and which can be taken from the surface reference of the surface point at the surface, or you can say that there is a net displacement based on the bonding surface, upper bonding or lower bonding surface. Then B is your dip slip. So, one is your slip along the dip of the plane, and another is along the strike. So, this part is the basic fundamental of structural geology. Usually we take that if there is a sort of an folding of the beds, okay, then the imaginary plane which has been drawn across this, okay, that will be horizontal. This will be your strike. The intersection will be intersecting will be your strike. Okay, so this is your strike, and perpendicular to this will be your dip direction, and the amount which you take with respect to horizontal will be your, that is your angle, is your amount of dip. So, this is a basic part of the structural geology. So, movement along the dip, movement along the strike. Okay. So, dip slip is your B. Okay. So, B, if you see, is if you try to figure out here, is this one. Okay. This is your B. Okay. So, this is your B. So, B is the dip slip, and then you have more of the components here, that is your C, that is your strike slip. Okay. How much slip was along the strike, because this blue line arrow shows your strike. Okay. Then you have the vertical throw. How much is the vertical throw? That is your D. Okay. And that is again with the reference point what we were talking about in terms of the bedding contact, or you can say the layer bonding surfaces. Okay. Then you have horizontal throw, which has been taken by your E, the total horizontal component of the net slip. Okay. That has been horizontal throw. Then have heave. So, if you require, you can recalculate, or you can extract this information from the section. Okay. But in quickly, if we want to evaluate this, then we should be interested in that how much is the dip slip and how much is your uh, strike slip component in this. Okay. So we can have the other combination also, thrust and strike slip also in many cases. Okay, we will come across. Now let us move to the tectonics and the type of deformation we will come across in the Himalayan zone, where you have a typical, we say that, a compressional tectonic environment. But that is not true actually, that always you will be seeing this compressional tectonic environment, or in compressional tectonic environment you will always see reverse fault and thrust faults. Okay, that is not possible because the strike of the fault with respect to the ongoing deformation vector will change and can result into an oblique convergence. Okay, so this oblique convergence may result into your strike slip. So if we quickly look at the topography, anyway I am not going to go into that much of detail on this, but mostly what we have observed in terms of while mapping the active faults, that in the eastern side we mostly see thrust fault on uh, the eastern extreme boundaries. We see a strike slip fault, okay, over here, and then we have thrust faults, or we can say the reverse faults. Okay, but at the same time we also see an extension which is going on here, plus we have a major fault lines. I am trying to put roughly, very roughly here, and then we have over here we see a sort of an strike slip faults, and that is your, this one is your Karakoram fault. Okay. So we have extension, we have strike slip, and as we move from here, some faults shows a typical of strike slip, plus we see also thrust faults. Okay. So deformation pattern, what we have seen even in strong compressional tectonic environment, varies from place to place. Okay, and that is because of the shape of the your tectonic plates, which is converging with respect to one another, and plus the direction of your stress pattern, how it have the relation with the strikes of the faults. Okay, or the weak zones. So that part what we have tried to understand. This has also been seen in GPS. Okay, the ongoing GPS measurements also shows that the western portion of the Indian subcontinent is having, or we can say that the Himalayan zone is showing an oblique convergence. Okay. So in India, if we look at broadly, then we all know, as I told, that this the eastern side is your right lateral strike slip, whereas if you go this side, then you have sort of an left lateral movement. Okay. So this you can keep in mind that uh, the deformation pattern keeps changing with respect to the relation between the subducting plate or converging plate and overriding plate. Now coming to the major seismic events in Himalaya, but before going to that, if you just look at this figure, what we have tried, that there are couple of regions which we have also discussed in the plate tectonics part. They are active and they are hazardous. Okay. Like if you take the Andaman Nicobar, that area is capable of hosting earthquakes up to 9.2 to 9.3, which was experienced in 2004, and that had multiple earthquakes in the past also. So we have twofold threat from this is that strong ground shaking in this area, plus we have tsunami. And if you go to the western portion, then we have Makran subduction zone, which also have a threat posed as tsunami. So our Indian eastern coastline as well as the western coastline is vulnerable to air tsunamis. Okay, this is one. Other than that, what we have experienced is that on and the because why I say experience, 2001 was experienced by most of us. Okay, so other than this a region, the Kutch area, okay, Gujarat, and in particularly we can say the Kutch region, okay, is vulnerable to earthquakes which have been triggered there, and this is the list. Okay, so finally if we look at this part here, we have historical earthquakes uh, recorded and reported. 1885 Kashmir, 1555 Kashmir, 1905 Kangra, 1934 was Nepal, Bihar, Nepal, and then Upper Assam earthquake 1950, and then 2005 Kashmir earthquake, or you can say Muzaffarabad earthquake, and 2015 was your Gorkha earthquake. Okay. So we have records of past earthquakes and major earthquakes greater than 7.5 in this region. So we'll discuss more on this and the type of deformation in the next lecture. Till then, thank you so much. Namaskar.